Okay, so today I'm going to be looking at section 3.4. I'm going to start with problem 9. In section 3.4, we learned about the chain rule, which is a way that we can take the derivative of a function that is in itself made up of another function. So like in this example, we have w at r defined as the square root of r to the fourth plus 1. If w to the r was, if w at r was defined as simply the square root of r, then we would know what to do. We would rewrite that as r to the 1/2 power. So then we would find the derivative of that is equal to 1/2 r to the 1/2 minus 1, which gives us 1/2 r to the negative 1/2. Okay, so that's what we would do if the function was the square root of just a variable. But that's not the case. What we have is the function is defined as the square root of another function. So we start off by treating it just the same as if we were taking the square root of the variable. So I'm going to first come back up here and rewrite this as r to the fourth plus 1 to the 1/2 power. And then I deal with this. I take my power rule, 1/2 of r to the fourth plus 1 raised to the 1/2 minus 1. So that would be then raised to the negative 1/2 power. But now I have to deal with that inside function. So I have to then take into account the fact that my inside function also has a derivative. So I'm going to multiply by r to the fourth plus 1, the derivative of that inside function. Okay, so let's see what that derivative is. So I have 1/2 r to the fourth plus 1 raised to the negative 1/2 power. Now I'm going to actually take the derivative here. And when I do that, I see that I have 4r to the third. Then I need to take the derivative of the plus 1, and that would just be 0. So I don't need to include that. And I have this. Now I can clean this up a little bit so that I end up with the derivative of w at r is equal to 2r cubed over the square root of r to the fourth plus 1. Okay, all right, let's look at another problem here. Let's look at number 15. So this is another example of the chain rule. This time we have w of x is equal to 100 e to the negative x squared. And so again, we know that if we just had e to the x, we could take the derivative of that. So if w was just defined as e to the x, then w prime would also be e to the x. So let's come over here and use that fact, only now we don't have e to the x, we have e to this function, negative x squared, so we'll have to deal with that when we get there. So I have w prime at x, the constant multiplier is in the derivative, it just stays there. And then I have e to something, the derivative of that gives me still e to that something, so e to the negative x squared. But now I have to deal with that something. I have to take the derivative of it. So I multiplied my previous information by that derivative. So now I'll come in and take that derivative. So I have 100 e to the negative x squared. And I have the negative bring down the power of 2, negative 2x. It's 2 minus 1 is just 1, so the exponent on the x is just a 1. Now I can clean this up a little bit more. Negative 2 times 100 is negative 200 x e to the negative x squared. And that is my derivative. Okay, so there's a couple of examples. Let's look at another one that is a little bit more complex. Let's look at problem number 19 from section 3.4. And problem number 19 tells me that I have f at t defined as t times e to the 5 minus 2t. Okay, so notice I said it's e times something else that has, t times something else that has that t in there. So I see I have essentially here two functions being multiplied together. I have t and I have e to an exponent that has a t in it. So I will have to use the product rule. And then I will also need the chain rule because it's not simply e to the t, it's e to this other function more complex than just t, which is 5 minus 2t. So I'm going to first deal with the product rule. The product rule tells me that f prime at t is equal to the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of that second function. So let me go through now and take these derivatives. So f prime at t equals, well, the derivative of t is simply 1. So I'm left with e to the 5 minus 2t term here. All right, let's go to the next piece of information we have. I have t multiplied by the derivative of e to the 5 minus 2t. So I have to find the derivative of this expression. Like I said, will involve the chain rule. So first I know that e to the anything, the derivative of that is e to that amount. So I have e to the 5 minus 2t, but then I have to deal with that 5 minus 2t by taking the derivative of that. Okay, so again, the derivative of this, I used the chain rule and came up with that. So now you see I still have one derivative that I need to take before I can do my cleanup. So I have f prime at t is equal to e to the 5 minus 2t plus t times e to the 5 minus 2t. And now I'll take the derivative of this last remaining term. The derivative of 5 is 0, so I will have essentially 0 minus, and the derivative of 2t is 2, so I have minus 2 there. Okay, so now all that's left is just a little bit of cleanup. I can see that in both of these equations I have this common term, so I will factor that out to the front, giving me e to the 5 minus 2t. And then I'm going to multiply that by, so when I factor e to the 5 minus 2t out of this term, I'm just left with a 1. And then in this second term, when I factor out the e to the 5 minus 2t, I'm left with a negative 2t, so I will have minus 2t. And that is my final answer for the derivative of that function. All right, I want to do one more from this section. I'm going to do problem number 37. I'm going to flip to a new page just in case I need the space. So problem number 37. I start with this function y equals 1 over e to the 3x plus x squared. And then I'm going to start by rewriting that as e to the 3x plus x squared, all to the -1 power. So again, you can see that I have here a situation where I'm going to need the chain rule because I have essentially a power of -1, but my base for that power is this more complex function. It's not simply x to that power. So I'm going to start by taking y prime, bring the -1 to the front of e to the 3x plus x squared, all that to the -2, so that use the power rule. And then I have to multiply that by the derivative of that inside portion. Okay. All right, so now let me actually take that derivative. So I have -1 times e to the 3x plus x squared to the -2. The derivative of this term right here, I would take the derivative of the first term and add it to the derivative of the second term. Now I see when I go to take the derivative of this first term, that in itself is also a composite function because it's not simply e to the x, it's e to the 3x. So that will cause me to use the chain rule once again. So you can see in this problem, I'm having to use the chain rule twice. I used it first here, and now I'm going to have to use it again on this term. So let me write that out. So I have the derivative of e to the 3x is going to be e to the 3x times the derivative of that term, 3x. Excuse me. So I'll come back and take that derivative later. I just want to write out what I need to do now, and then I'm going to continue on because really my task right now is to take this derivative. So that's just the first portion of that derivative. Now I'm going to go deal with the second portion, which says plus 2x. Okay, so now I have this still to deal with, and then I can clean up. So I have negative e to the 3x plus x squared to the -2. And then that's all multiplied by e to the 3x. And then the derivative of 3 to the x is simply 3 plus 2x. So now I want to clean this up a little bit. I'm going to turn it into a fraction. So in my denominator, I'd have e to the 3x plus x squared. In my numerator, I'd have 3 times e to the 3x plus 2x. And I've got this negative sign out in the front, so I can deal with that by simply putting the negative sign in the front of my fraction. Okay, that's it for that. Hopefully this helps. If you would like to see more